Graph the following functions using your knowledge of the parent function and transformation rules. Do not use a graphing calculator. Well, the parent function is given, and we want to take a look at this equation, and we want to identify each transformation. And the way that we're going to do that is we're going to read our equation going left to right. The negative in front of the function tells us that we're going to reflect our graph over the x-axis. So as we start to graph this without using a calculator of any help, all that that's going to do for us is that's going to turn our graph upside down. I'm going to start with the vertex, and the vertex is going to remain 0, 0. But instead of the point 1, 1, our point is going to be 1, negative 1. Instead of our point 2, 4, our point's going to be 2, negative 4. Instead of the point 1, negative 1, it's going to become negative 1, negative 1. Instead of our point negative 2, 4, it's going to become negative 2, negative 4. Again, we reflected the graph over the x-axis. You can see that it's kind of turned upside down. Well, there's our first transformation. As we are reading the graph from left to right, then we see inside the parentheses we have plus 5, and think about what that transformation means. And maybe you think of it in terms of a vertex. But what this means, with just respect to the plus 5, is that we're going to move our graph left 5. So we're going to take the blue graph that we just graphed. We're going to move every single point left 5 spaces. I'm going to start with the vertex. 1, 2, 3, 4, 5. So 0, 0 became negative 5, 0. 1, negative 1 becomes negative 4, negative 1. 2, negative 4 becomes negative 3, negative 4. Negative 1, negative 1 becomes negative 6, negative 1. And negative 2, negative 4 becomes negative 7, negative 4. And there's our second transformation. Thirdly, and lastly, we have minus 2 in our equation. And we're reading the equation from left to right. Minus 2 means that we're going to take this green graph now, and we're going to move every point on that green graph down 2. Again, starting with the vertex, so negative 5, 0 becomes negative 5, 2. Negative 4, negative 1, if I can get that here, negative 4, negative 1 becomes negative 4, negative 3. Negative 3, negative 4 becomes negative 3, negative 6. Because our point negative 6, negative 1 is going to become negative 6, negative 3. And negative 7, negative 4 is going to become negative 7, negative 6. And there's our final graph. Just as an aside, what's the domain of this function? And it's the same for all of our quadratics. It's all reals. It's the range that we need to be a little bit more careful with. And what the range says is that we ask ourselves, do we have a high point or do we have a low point on the graph? We have a high point. And when you're dealing with the range, you start with the lowest value, which is the graph is pointing downward. So we're going to start at negative infinity. And we're going to keep going up and up and up and up until we get to the y value of our vertex, which is -2. And because that point is on the graph, we have a bracket. Just an aside, but I don't want you to forget how to deal with the domain and the range. Again, our goal today is to graph these functions without a calculator. And in order to do that, read the graph left to right to do these transformations. So the first transformation that we see in this question number 2 is we see the 1/2 in front of the function. Well, the 1/2 in front of the function means that we're going to vertically compress this graph. And we're going to compress it by 1/2, and it's a vertical change, which means only the y value changes. And as we start our graph, however, our vertex is still going to be 0, 0. Because 0 times 1/2 is 0, the y value. So now that we know that, then the next part here is we're going to go one space to the right, but instead of going 1 up, we're only going to go a 1/2 up. It's 1, the vertical value, the y value 1, times 1/2. And it's very hard for me to put in here, but your point that you're graphing is 1 and then 1/2. Over to the right 1, up a 1/2. We can see it a little bit better on the next point, because on our parent function, our next point is 2, 4. Well, the 4 is the vertical distance. We're going to multiply 4 times 1/2, and 4 times 1/2 is 2. So we're going to go 2 spaces to the right and 2 up. And some of you even see the symmetry of this graph. You probably don't have to think much on the other side, because it's the same sort of computations. We're going to go 1 space to the left, but now we're only going to go up a 1/2. So -1, 1/2. And then -2, 4 becomes -2, 2, because again, we cut the y value in half. It's very hard to see up here on the smartboard, which is why I'm trying to save those values of those points. So our next transformation, there's a negative in front of the function. Sorry, it's not in front of the function, it's inside of the function, which means that we are going to reflect over the y-axis. And the thing is, when I draw this picture, you're not going to be able to see any change. It's going to look exactly like my blue graph. As I talk through, I still think that this one's going to be hard for you to see on a video, so you might want to ask your teacher if you're watching the video of these notes. But we're going to start with 0, 0 still. Then our next point would be 1 space to the right and a 1/2 up. So we'd go 1 space to the right and 1/2 up. But then you have to reflect this graph over the y-axis. So I'm going to try to put this point in right there. That's the right side of the graph, folded over to the left side. That's the reflector of the y-axis. Same process. We're going to go 2 spaces to the right and 2 up. That's the original point. We're going to take this point and we're going to fold it over the y-axis for the reflection over the y. And the same process would happen. The values on the left would land on the right side when we fold the graph in half. Again, it should be the exact same picture as the blue graph. And then we can finish this problem here with our -4, which is the transformation of down 4. I'm going to start with the vertex when I move these down 4. So 0, 0 is going to become 0, negative 4. 1, 1/2 is going to become 1, 3.5. Negative 3.5. 2, 2 is going to become 2, negative 2. Let me see that again. Yes. 2, negative 2. Negative 1, 1/2 is going to become negative 1, negative 3.5. And negative 2, 2 is going to become negative 2, negative 2. We moved each of the points on the green graph down 4. And there's our picture. If you take these step by step, identify the transformation graph, identify the next transformation graph, identify the next transformation graph, hopefully that will work for not using a calculator. That's our goal, is to identify the transformations and get a graph without using a calculator. Problem number 3. Probably my favorite problem on here. And the thing that we need to realize in this one, in terms of transformations, is that negative does something to the graph, and the 2 does something to the graph. They are separate pieces when we draw the picture. So only the negative is what I'm looking at first. And that's going to be the reflect over the x-axis. And we've done that. We did that on the first graph, I think, one of them. We're just going to take all our points and we're going to turn them upside down. 0, 0 is going to stay the same. 1, 1 is going to become 1, negative 1. 2, 4 is going to become 2, negative 4. Again, we're reflecting our graph over the x-axis. Negative 1, 1 is going to become negative 1, negative 1. Negative 2, 4 is going to become negative 2, negative 4. There's our reflect. That's only the negative. Now we'll deal with the 2. And the 2 is a vertical stretch. Remember, when we're dealing with the vertical stretch or vertical compression, only the y values change. So when we look over here at this one, 0, 0 is still going to stay the same. Our vertex is still going to be the same. But instead of this point 1, negative 1, the y value, the negative 1 part of that point, is going to be multiplied by 2 because it's a vertical stretch of 2. That number out in front of the x squared. So it's going to be negative 1 times 2. We're going to graph a point of 1, negative 2. And the point 2, negative 4, we're going to take the y value. Negative 4 times 2, which is negative 8. So it's going to be 2, negative 8. To the left of this, we have negative 1, negative 1. Negative 1 times 2, it's the y value, times 2. And negative 2, negative 4, it's our next point. We're going to take the negative 4 from that point and multiply it by 2. And we get negative 2, negative 8. And there's our vertical stretch. By the way, just as an aside, one way that you can look at a graph and determine the vertical is if you know the relationship in the parent function, 1 space to the right and 1 up, if you're going more than 1 up or 1 down, then you might have a stretch. Or if you're not on a whole number part, you're probably going to compress. But without getting lost in this graph here, the last part, the last transformation is the plus 5, which means that we're going to go up 5. I'm going to start with the vertex. 0, 0 is going to become 0, 5. 1, negative 2 is going to become 1, 3. 2, negative 8, we're moving this up 1, 2, 3, 4, 5. It's going to become 2, negative 3. Negative 1, negative 2 is going to become negative 1, 2. And negative 2, negative 8 is going to become negative 2, negative 3. And here is our picture. Again, let me stress. One transformation, then draw the graph. Next transformation, draw the graph. Read the equation left to right. As we finish our last graphing question here, the parent function, sorry I don't have that one drawn in, but I'll get that drawn in, is 0, 0. It's drawn in on your paper, at least it should be. But what are our transformations here? Well, the first one, vertical stretch. And that's because of the 3 out in front of the function. 0, 0 is going to stay the same. But instead of 1 space to the right and 1 up, we're going to go 1 space to the right and 3 up. 1 times 3. Instead of 2 spaces to the right and 4 up, we're going to do 2 spaces to the right and 4 times 3, 12 up. So it's going to even go off the graph here. And my board's a little bit disoriented, so I can't get that in there. 1 space to the left, and instead of 1 up, we're going to go 3 up. And 2 spaces to the left, and instead of going 4 up, 4 times 3 is 12. And again, I can't get that in there. I'm trying not to make it too pointed. I know my picture looks pointed there. Next one, minus 4, means that we're going to go right 4. And because I'm running out of time on this problem, I'm going to go over here 1. And right 4 up 1 gives us a vertex. Right 4 up 1. And we already have the pattern on here. And we can't even fit all of these points on the graph. But from the blue graph, we went 1 space to the right and 3 up. So now on our red graph, 1 space to the right and 3 up. And 1 space to the left and 3 up. And our other points that are way off the graph, we went 12 up. We're going to have to move that up. So it's way up here off the graph. But at least we can get these 3 on our picture here. So the graph of the parent quadratic function and a transformation of the parent function are given. List the transformations that occurred and then write the equation of the transformed function in vertex form. Well, what I can recommend on these is that we start with the vertex. In the blue graph is the parent function, and the purple graph is the transformed function. And if we look at our parent function, 0, 0, our new vertex is now negative 3, negative 4. And what we did to get there is we moved our graph left 3, and then we went down 4. And as we take a closer look at this, it doesn't look like anything else happened. We definitely did not reflect the graph over the x-axis, because our quadratic, our purple graph, would be upside down, and it's not. And we've been focusing on the vertical stretch and compress. And one thing that you can use to tell if there's a vertical stretch or compress is knowing the pattern of the function. in the blue graph, we went one space to the right from the vertex and one up. Well, in the purple graph at the vertex, we went one space to the right and one up. Since that pattern didn't change, we don't have any vertical stretch or compress either. And now that we know that, we can write our equation, which I'm going to write over here instead of on the line. And when we write this in vertex form, I'm going to put in the parentheses there. And it's going to be x. And since we went left 3, what happens is we're changing the sign. Left 3 is -3. Change the sign. And then down 4 is keep the sign. And there's our equation of our function. Let's try another one. As you see, let's start with the vertex, and then we can deal with the other transformations. Well, from the blue graph, which is our parent function, to the purple graph, our vertex now, we went right 4 and up 3. Just identifying the vertex, right 4, up 3. But we actually do have 2 more transformations in this graph. And the next one I look for is the reflection. And as we can see in this particular picture, our graph is upside down. The purple graph is upside down. And what that means here is that we're reflecting the graph over the x-axis. And it's really hard to see in a picture a reflection over the y. But here's the reflection over the x. The last thing that we need to check for is, do we have a vertical stretch or compress? And again, in terms of pattern, from the parent function, start the vertex. We went one space to the right and one up. Well, over here in our purple function, we went one space to the right, but we went 2 down. And because we went 2 down, instead of 1 down, the 2 down, the down part, is the reflection. But the 2 means that we vertically stretched this graph. And in fact, I'm not picky about this, but I'm going to write x2 for times 2. And after we identify those transformations, then we can finish here by writing the equation. I'm just going to start with the vertex. Well, we went right 4. So I'm going to write x minus 4. Because remember, when we're identifying the vertex, we go change the sign. And then we say keep the sign. That takes care of the right 4, the up 3. The reflect over the x-axis is determined because there's a negative out in front of the function. If it were reflect over the y-axis, it would be inside the parentheses, but it's not. We're reflected over the x-axis, and that's the outside of the parentheses. The vertical stretch, or compression, as the case may be, is on the inside, it's on the outside of the function for vertical stretch or compress. The inside would be horizontal, and we're not talking about horizontal. So vertical stretch is outside. So notice, negative is a piece, the 2 is a piece, then the parentheses is a piece, and then the 3 is a piece. And by piece, I mean those are separate transformations of our graph. Lastly, once again, start with the vertex. If we take a look at our vertex here, we went 1, 2, 3, 4, 5 left. And we went down 2. So there's a vertex. We did not turn our graph upside down. So we don't have a reflection. So let's look and see if we have a vertical stretch or vertical compression. And we went one space to the right and one up. But in our purple graph, we went one space to the right and it looks like 1/2 up. And because we only went a half up instead of a full value up, this is going to be a vertical compression. And because we are writing the equation, I'm not picky about the x 1/2, the times 1/2, because it shows up in the equation. We get y equals, well, let's put in our vertex here, 5 left. It's going to be x plus 5, because remember, change the sign, keep the sign, and then our vertical compression again happens outside of the function. It's going to be the 1/2.